Hello, my name's Chris Harris and I'm from Allery Chemistry, and welcome to this video on EDEXCEL Topic 11 Equilibrium 2. So in this video we're going to specifically look at the information you need to know for the Equilibrium 2 topic for EDEXCEL. So if you're studying EDEXCEL, then this video is ideal for you because it has all the information you need to know for revision purposes, and no information that you don't need to know. So in other words, you don't have to look through it and think, is that on the specification or will that be in the exam? So everything that you've seen here is dedicated to EDEXCEL. There is the full range of EDEXCEL videos for year 1 and year 2 on my Allery Chemistry YouTube channel. They're all for free, all readily accessible on there. All I ask is that you hit the subscribe button to show your support. That would be fantastic. Also, if you would like a copy of these slides, because these are just PowerPoint slides that I'm using here, but if you'd like a copy of what's in here for the video, the great revision material, you can use them on your smartphone or on your tablet. Then if you click on the link in the description box and you can purchase them from a test shop, they're really good value and you can do whatever you want with them. You can print them off, use them as revision notes, anything like that. So they're ideal for, like I say, for EDEXCEL. What you'll also find as well is that the information in this video is mainly going to look at revision notes for EDEXCEL. It's obviously just as important to practice your exam technique as well, because it's one thing knowing knowing the content, it's another thing actually applying it. It's a bit like, I suppose, learning to drive. If you get the highway code, it tells you the rules of the road, but it doesn't, just because you read it from front to back doesn't mean you can hop in the car and start and drive around. Otherwise you may cause injury to somebody or anybody who is learning to drive, I suppose, at the moment. So it's important to practice exam techniques. So go through your exams, answer the questions, and make sure that you're comfortable with what the question's after, and that you're writing concise answers with all your keywords in there. That's very, very important. I have done some videos in Allery Chemistry YouTube channel, and the videos cover exam technique. They go through the questions and make sure that you can answer them, and it goes through all the answers as well. Go through the exam technique, so the exam paper walkthrough. So if you just have a look on Allery Chemistry, and you can see some of the some past papers that I've done there as well. Okay, so let's get started. So let's say this is dedicated to the specification. So they're the specification points that it meets. There's only 5 of them, but it's quite a big video, this one. So by all means skip to the bits that that may help you. But so there's loads of information in here, like I say. So let's start with reversible reactions. So reversible reactions is where a reaction can go forwards and backwards, and it has this arrow here, and you would have seen this arrow before. It's the forward and reverse arrow, shows an equilibrium reaction. As a generic example, we've got A and B producing C and D. So let's have a look at a graph of concentration against time, and this helps us to plot an equilibrium reaction. So the forward reaction, initially the reactants are used up. So you can see here that we're starting with a really high concentration, reactants are used up, so the concentration decreases there. And then if we look at the backwards reaction, initially the reactants are reformed slowly, but speed up as the concentration of products increases. So you can see here that we've got our line that starts at the bottom here. So the green line, so we've got no concentration here, but obviously as the reaction proceeds, the amount of product starts to increase. Okay, so you can see here at this point, this is the point where the rate of the forwards reaction equals the rate of the backwards reaction, and we call this a dynamic equilibrium. And this means that the concentration of each substance remains constant. So this is at the point where both your reactant and product lines start to flatten out, and we call that we say that an equilibrium has been reached. Now we can't get this confused, because this is not the same as the amount of reactant and product. This is actually to do with the concentration of them that are the same. So you might have a different amount of each reactant and product. So make sure you're using your key terminology correctly. That's vitally important. Okay, so this only occurs in a closed system. So we call this a dynamic equilibrium. So dynamic equilibriums only occur in a closed system. all that means is that we have a system where nothing can enter and nothing can escape. So as an example here, we've got a beaker and we've got a lid on top of that beaker. So any reactions in there are actually maintained in that beaker. Okay, so let's look at a constant. So we're going to look with, obviously we know what equilibrium is, and we know what the reversible reaction is, and reversible reactions and equilibrium obviously go hand in hand. So really what we're going to look at is we're going to build upon stuff that you've already seen already in year 1 EDEXCEL, and we're going to build them and add extra bits to it. So Kc is the equilibrium constant, and we're going to use this to work out, do a bit of maths and use concentrations, etc. So it can be worked out from the molar concentration in a reaction. So the molar values in front of each species are powers of the Kc expression. The Kc expression is set up like this. So you can see that we've got Kc equals C squared D. So these are your products divided by your reactants, which are A and B. And you can see the powers on your Kc expression actually relate to the number of moles on the reaction that you can see there. So there you go. So it's products over reactants. And our square brackets is an important point as well. This just means the concentration of. So this is vitally important because when we're working out, and you'll see later on in some examples, we've got to make sure that the numbers we're using in the Kc expression is concentration. We're not looking to use moles. We're not looking to use volume in this. You'll see some volume ones later. But we're not looking to use that. It's only got to be concentration. So let's have a look at an example. So we're going to write the Kc expression and calculate the value of Kc for the following reaction. So we've got the concentration of SO2 being 0.4 moles per dm cubed, the concentration of O2 being 0.2 moles per dm cubed, and the concentration of SO3 being 0.8 moles per decimeter cubed. And you can see we've got our reaction that's written down at the bottom there. So the expression is going to be products divided by reactants. So our products is going to be SO3, because we've got a 2 in front of the SO3, we're going to do SO3 squared in our Kc expression. Our reactants go on the bottom, so we've got O2 and SO2 squared. The reason why it's SO2 squared is because we've got lots of SO2 molecules in our original equation. So that's our expression. So now we've just got to do the calculation. So we substitute the numbers. So we've got 0.8 is the concentration of SO3. We've got 0.2 and 0.4 at the bottom there. Remember to include our squared functions in there as well. And then we should get a value of Kc of 20. So the units are actually quite important as well, obviously. But the units can change and we have to calculate the units. So you can see here, units for Kc, we just write the concentration, or the units of concentration on the top and on the bottom. And we take into account any squared functions as well. So let's have a look at this example where we've got 0.8 squared. Because there's a squared there, we have to write moles per dm cubed twice. So that's the concentration. And at the bottom, we've got 3 lots of moles per dm cubed because we've got a 0.4 squared and we've got a 0.2. So we've got we've got a total function of 3. So all we do is we cancel the ones on the top and bottom, and any that are left over that are on the bottom of the line, we invert them. So we shift them up back onto the top line, and we invert the actual unit. So let's have a look. There we are. So we cancelled the top and bottom. We had moles per dm cubed left. We switched that onto the top line, and so that means we have mole to the -1 dm cubed. So you can see there we've inverted the numbers. So before there was mole, now it's mole to the -1, and there was dm -3, and that's now dm3. So all we do is invert it, and that is the unit. So it's as simple as that. So it's not too bad. Okay, so let's look at the Kc equilibrium constant for a homogeneous reaction. Okay, so you'll see homogeneous in a minute, but homogeneous basically just means that everything is in the same state. So homogeneous, same state. So the Kc expression can be worked out from the molar concentration in a reaction. So let's have a look at this particular example here. So remember that we've got our expression here. The powers, remember the front, so the number of moles for each substance in front corresponds to the powers on the end of your C and A, as you can see on there. So remember it's products over reactants, and the square brackets means the concentration of. So this is just information that we had from our previous slide. So let's write out the Kc expression for the following reaction. So we've got 2SO2, which is a gas, plus O2, which is a gas, going to 2SO3 gas. Okay, so they're all gases because it's a homogeneous reaction, so there's no difference here. So there we are. So that's what we were saying before. Homogeneous reaction, all of them in the all reactants are actually included in the Kc expression. You'll see example later where it's heterogeneous and we don't include everything, but everything that's in here, all the reactants and products are actually included in our Kc expression. So the expression, therefore, is SO3 squared divided by O2 times by SO2 squared. So here's our Kc expression here in the green box. Okay, so we keep everything the same. So let's contrast that with a heterogeneous catalyst. So this is where we've got the physical states of our reactants and products are different. So we're going to do exactly the same. We're going to work out our Kc expression. But notice here we've got the molar values of A, B, C, and D, and we've written our Kc expression. But notice what we've done is we've missed out B from our Kc expression. So this is because your solids are pure and your liquids are not included either. Anything which is a pure liquid or a solid, anything which is which can't be effectively can't be included within a Kc expression is obviously omitted. So anything that's solid or pure liquids that you see in an equation, you do not write them in your equilibrium constants. You keep them the same. Okay. So what we do is you write the Kc expression for the following reaction. Let's link this with a real life reaction. So we've got carbon, which is solid, oxygen, which is a gas, and carbon dioxide, which is a gas. So this is a heterogeneous reaction. You can see here that we have a solid and we have a gas and a gas. So let's look at the expression. Kc equals CO2 divided by O2. So it's products divided by reactants, but our carbon is solid. Solid isn't included in our Kc expression because we assume that the concentrations of solids and pure liquids remain constant throughout the reaction. Okay, so let's look at the concentration of species in equilibrium and see how we can use them, see how they could be worked out before we actually work out Kc. So we're going to use this method here. Now you might use a different method and you'll see it later on. I use a method called an ICE method, so initial change in equilibrium, and it just helps us to work out the concentration of a species in equilibrium. So let's have a look at this example. So we've got nitrogen dioxide decomposes according to the following reaction. So we've got nitrogen dioxide forming nitrous oxide, nitrogen monoxide, and that's plus oxygen. Okay, all of them are gas. All of them homogeneous systems, are all in the same state. Okay, so excuse me. So we've got 33.2 grams of NO2, and that was heated in a vessel with a volume of 9.65 deciliters cubed at 450 degrees Celsius, and 6.88 grams of O2 were found in the equilibrium mixture, and we need to calculate the value of Kc. Okay. So what we've done here is we've drawn a table. Now the table shows the number of moles of NO2, NO, and O2. So we've just literally written down our products and reactants that will appear in the Kc expression. We've written them down in the table there. And along the left there, you see we've written initial, change, and equilibrium. So this, if we take the first letter of each, spells out the acronym ICE. It's a cool topic. Right, anyway, next. So there you go. So we're using the acronym ICE, initial moles, change in moles, and equilibrium moles, and we'll see how that works. Okay, so the first thing, what we need to do, when we draw out this table, is we need to fill in the numbers for the initial side. Okay, like I say, you might use a different method. I think this is I like to use methods, if you've seen me other videos as well, I like to use methods which are quite structured. It might involve drawing things out like this, but it means you know exactly where things are. It's nice and clear, it's nice and neat, and you can see what's going on. Also, that's really useful because remember, you have to sit an exam. So the exam is going to be fundamentally based on you trying to prove to the examiner that you know what you're talking about, which seems a bit strange. So you might know that in your head, but you've got to portray that to the examiner. So showing your work in a nice, clear way really helps the examiner to give you that mark. There's no doubtful marks. There's clarity in your answer. So this is actually it's good practice to get into this. So moles of NO2 is mass over mR. Okay, so we need to work out the number of moles in our initial substances. So we've got moles here of our NO2, which is here, and we know that we've got 33.2 grams of NO2, as you can see. So moles of NO2, mass over mR, mass is 33.2, divided by the mR of NO2 is 14 plus 16 plus 16, and then we put that into our table there, which we get 0.72. So you can try that, put that into your calculator, see if you get the same answer, and you should do. The products are 0. Now, the reason why they're 0 is because we haven't actually made any. This is right at the start, initial. We haven't made anything yet, so we should have no products whatsoever. We've got loads of reactant, but no products. Okay, so the moles, the next thing we need to do is to work out the moles of oxygen at equilibrium. And what we're going to do is mass divided by mR. So the mass is 6.88 grams because we've been told that we produce 6.88 grams of oxygen, and we divide that by 16 plus 16 because it's O2, and then we get our change. So this is how much it's changing by, plus 0.215. So we're producing, so there's a change of 0.215. That's how much we've produced in moles. So therefore, at equilibrium, we should have 0.215 moles at equilibrium. So what we're going to then do is now use the molar ratio in our initial equation that we've been given to work out the changes for other species. What we've got to remember is that our product will increase. Okay, so we're producing more products, so therefore that will always increase, and all reactants will always decrease because we're using them up. Okay, so when we look at the change column in these examples, just remember that products increase, reactants decrease. Okay, so let's look at NO. So NO, we've got a change of 2 lots of 0.215. Now we know it's 0.215 because this is the mole that we worked out for O2. We've got 2 lots of them, so the change is going to be twice as big. So it's going to be 0.430. So the total amount of NO at equilibrium is 0.430. That's the number of moles. And then finally, we need to do exactly the same for NO2. Now, the number of NO and NO2 is the same. The molar ratio is 2 to 2. So that means that we have 2 lots of 0.215. That's the same here. It's 0.430, but it's going to be a minus. The reason why it's a minus is because we're losing our reactant. It's been used up, so that's always going to be a minus. Now, we had a number in here already, 0.72. So it's just 0.72 minus 0.430, and so we should have 0.29 moles of NO2 in equilibrium. So then we need to calculate the concentrations. So concentration, remember, here we've got the number of moles, which is here, and we're dividing that by the volume, which is here. Now the volume's already in decimeters cubed, so that's fine, 0.65. So then we work out concentrations of every species that we've got in that table. Okay, because remember, in the Kc expression, we must use concentration, not moles. So our Kc expression is NO squared times O2 divided by NO2 squared. So the calculation, put all our numbers in. So remember, it's products divided by reactants for Kc, and our Kc value is 0.050. Obviously, we need to work out units as well, because that's just as important. So again, just like we've mentioned before, our units is 3 lots of concentration on the top, because we've got squared and a single one there, so it's mole per dm cubed 3 times, divided by moles per dm cubed twice, because we've got a squared function there. So we cancel them off, and then we're left with moles per dm cubed, as you can see on the top. So that is the units that go in there. So we don't need to invert them because it's already sitting on the top line. That's where the excess is. Okay, so you might have a different method to this, but like I say, I like to keep things structured and ordered and make sure that you know exactly where things are. It just makes it a lot neater. And then if you do make a mistake, you can go back and you can see, right, well, say if this number's not right, then you know why, because you've actually included your work in there. Okay, so we're going to use Kc to or we're going to work out an unknown concentration at equilibrium by using Kc. So let's look at a reaction, and this reaction took place, and at equilibrium, equilibrium was allowed to be established, and ethanol reacts with ethanoic acid. Now at equilibrium, the concentration of ethanoic acid was 1.8 moles per decimeters cubed, and ethanol was 3.2 moles per dm cubed, and the value of Kc is 3.5 at 25 degrees Celsius. Calculate the concentration of the products at equilibrium. So you can see here that we've got our reaction there. So we've got our carboxylic acid, which is our ethanoic acid here. With our ethanol, this is our alcohol. We're forming our ester and water. So you you may have seen this already. It depends on which order you're doing things in at school or college, or if you're doing it independently. But this is an esterification reaction. So we're producing an ester here. So the expression is CH3COOCH2H5 and water, and we have CH3COH and C2H5OH. That's our alcohol on the bottom there. Okay, so it's always got to be products divided by reactants, remember. So the calculation, what we're going to do is just substitute everything that we've got. So we've got the concentration of our carboxylic acid here. This is our ethanoic acid, which is 1.8, and we also have our concentration of our alcohol or ethanol here, which is 3.2. We have our Kc value of 3.5 because it's just been told that, but we don't have the concentrations of our ester or of our water. So the calculation, all we do is we rearrange it. So we get our concentration of our ester and water. So we take these here, and this equals, this is 3.5 times 1.8 times 3.2. We put it in our concentrations. This is the value that we're working out here. So we're rearranging, basically we're making the top line the subject to get these figures here. So we've got a concentration of our ester multiplied by the concentration of water will give us 20.16. So we'll just multiply them numbers there to get 20.16. So we know that the concentration of our ester equals the concentration of water. So what we can say is that the concentration of one of these is going to be the square root of our answer that we got here. So that's going to be 4.49 moles per decimeters cubed. So therefore, the concentration of our ester is going to be 4.49 moles per dm cubed, and the concentration of our water is also going to be 4.49 moles per decimeters cubed. So it's all going to be the same in terms of the products that are being formed. Okay, so you've got to remember to square root that. It is common. It is common for people to miss out the square root bit. Remember, you've worked out the concentration of both species here, so you do have to square root it. Okay, so let's look at another example, and this is quite similar in the sense that we're using a Kc type expression, except here we're going to use gases, and we're looking at pressures, and in particular partial pressures and total pressures. So the total pressure in a reaction is the sum of the pressures of individual gases that make that reaction up. Okay, so this is what we call partial pressure. So that kind of makes sense, doesn't it? So let's have a look at some examples. So you may be asked to use information to answer questions like this. So SO2Cl2 decomposes into sulfur dioxide and chloride, so SO2 and Cl2 under heating. So you can see here, here's our reaction, it's decomposing, it's breaking down. At equilibrium, the reaction vessel contains 263 kilopascals of chlorine. The total pressure of the vessel is 7.14 kilopascals. We need to calculate the partial pressure of SO2Cl2, and we symbolize partial pressure by putting in P, so it's a lowercase p with a subscript here, which is SO2Cl2 at equilibrium. So that's how we symbolize partial pressure. So we know the total pressure is the sum of all the partial pressures. So total pressure must be the partial pressure of SO2Cl2 plus the partial pressure of SO2 plus the partial pressure of chlorine. So that's pretty straightforward. So we've got some numbers already. We know that the total pressure is 714 kilopascals. So that's the figure there. We don't know the partial pressure for SO2Cl2 or SO2, but we do know the partial pressure for our chlorine. That's 263 kilopascals. So we've been told that. So we know that chlorine has a partial pressure of 263. There's a 1-to-1 molar ratio with SO2, looking at our reaction just up there. And as this is a product as well, the partial pressure for SO2 is the same as Cl2. So we're going to complete the equation a little bit further and add in 263 to represent our SO2 as well. Okay, we can only do that because it's a product. We can't do it for the reactant. We can do it as a product because it's obviously the product has come from the same source. So then we simplify this equation, and so we're going to say, right, 263 plus 263 is 526. So we've got 714 equals the partial pressure of SO2Cl2 plus 526, and I think you know where we're going here. We're going to rearrange it, so to get SO2Cl2 as the subject, so we do 714 minus 526, and we get our partial pressure of 188 kilopascals. So you can see there, it's fairly straightforward. It's just the sum of everything equals the total pressure, which is fine. Just remember the bit in the red box there, which is referring to the molar ratio. Well, we could already do that because we were working out another product as well. We can do it for a reactant, but it must be must compare for reactants only and compare products with products only. So we can't work out. In other words, we can't work out the moles of a reactant from knowing the moles of a product, and like a normal traditional way in which you could in a standard equation, like for titrations. Okay, so let's look at mole fractions. So the partial pressure of a gas, as we've just seen there, is calculated using mole fractions. And a mole fraction is just the proportion or a fraction of a gas in a gas mixture. So let's take a generic example. So we've got 2D, and that's forming E plus F. And here we have 4 moles of gas, okay? 2 of them are D, and so the mole fraction for D is a half, okay? So just to work out for 1D, it's going to be a half. So you need to know the following 2 equations when dealing with mole fraction calculations. So the first one is the mole fraction of a gas is the number of moles of gas divided by the total number of moles of gas in the mixture. And then the partial pressure is just the mole fraction of the gas that we've just see there in the previous equation, multiplied by the total pressure in the mixture. Okay, so there's 2 there. So let's look at some examples here. So 3 moles of SO2Cl2 is heated. The equilibrium mixture contains 1.75 moles of Cl2. The total pressure is 714 kilopascals, as we've seen. What is the partial pressure of SO2Cl2? So, and we've got our equilibrium reaction there, which is SO2Cl2 in equilibrium to form SO2, sulfur dioxide, and chlorine. Okay, all looks rather familiar. So, first of all, we need to draw our ice table out. Okay, such a cool table. I know I've said that one already. Let's move on. So first draw our ice table and write the initial moles of each gas. So here we've got our reactants and products at the top line, as you can see there on our table, and we've got our ICE acronym down the bottom there. So initial moles, changing moles, and equilibrium moles. So we know that we've got 3 moles of SO2Cl2 because we've just been told that at the top there. Our products, obviously we don't have any products, and if you remember why, the reason why is because we haven't formed our product yet. So we wouldn't have any moles of any of them because we haven't actually started the reaction, because it would be in the initial column. Okay, so we know that we have 1.75 moles of chlorine at equilibrium. Okay, big difference between initial and equilibrium, remember. So this change is plus 1.75 because we're producing 1.75 moles of chlorine. Why? Because we were told that in the question. Okay, so the equilibrium moles is going to be 1.75, so that means the change is going to be an increase of 1.75 because we've started with nothing. So we're going to use the equation to work out our one-to-one, or to work out our ratio or stoichiometry. It's a one-to-one ratio. So the changes will be the same. So you can see here that the amount of SO2 is going to be plus 1.75. The amount of SO2Cl2 is going to be minus 1.75, because remember, we're using up reactants, so it's got to decrease as the reaction goes ahead. So it's minus 1.75. So we can now calculate our equilibrium moles. So we've got 1.75 of SO2 and 1.25 of SO2Cl2. Pretty straightforward so far. So the mole fraction of SO2Cl2 is 1.25 divided by 4.75. So this is your 1.25 here, but the 4.75 is the sum of all the equilibrium moles. So if we add up all of these here, that gets us 4.75. Obviously our 1.25 there is the equilibrium moles of SO2Cl2. So the mole fraction here is 0.263, so fairly straightforward. So then we need to work out our partial pressure. So partial pressure is our PSO2Cl2, which is our partial pressure, is basically 0.263, which is our mole fraction, multiplied by the total pressure, which is 714 kilopascals, and so therefore we've worked out our partial pressure. There. So our partial pressure, we put the numbers in, and we get 188 kilopascals. So there's a lot here, okay, but you can see using that ICE table massively helps, because actually it's giving you a lot of information. You can use it multiple times, not only to work out equilibrium moles, but obviously to also work out the sum of all the equilibrium moles in order to work out a mole fraction. So it is definitely worth the time drawing that out, and you can see everything there. Everything's laid out in front of you. Okay, so let's look at Kp, okay, our equilibrium constant. So partial pressures are used to work out the gas equilibrium constant Kp, as we've just seen there. So this may look familiar, okay, but we don't want to confuse it with Kc, which we've just seen before. It is similar, but we're using partial pressures here. So, and what we're using, obviously, if we're using partial pressures, we're dealing things in pascals rather than in moles per decimeters cubed, which is concentration. So there's a slight deviation away from that. So here's an example for writing a Kp expression. Okay, so we've got E, which is in gas form, F is in gas, G is a gas, and H is a gas. So because all these are gases, we can use the Kp expression here. So Kp is Pg, which is the partial pressure of G, the partial pressure of H, divided by the partial pressure of E and the partial pressure of F. And you can see here we've got our superscripts here, so our indices at the top. So that is basically dependent on what number is in front of G in the equation goes at the top there. So it's exactly the same as Kc in terms of how we work it out. And we've always got to put on there as well, just before we move on to this purple box, we've always got to put our products at the top, reactants at the bottom, no difference. Okay, so let's look at an example where we're going to work out the value of Kp for the following reaction, and we're going to have to give units as well, of course, because it's chemistry, so you've got to give units. So, given that the partial pressures are 324 kilopascals for A, 162 kilopascals for B, 182 kilopascals for C, and 182 kilopascals for D at equilibrium. So we need to work out the value of Kp. We do exactly the same. Always write out your expression. So a Kp expression, as you can see there, so it's always product divided by reactants. Put in the numbers, as you can see, there's the numbers there. So we just put 182 times 182 divided by 324 squared times by 162. The reason why it's squared is because A has got a 2 in front of it, as you can see in the original equation. So we get our Kp value of 1.95 times by 10 to the minus 3. So put all that in the calculator and you'll be able to see it there. And then obviously we need to work out our units as well. This is where it is a little bit different because we're going to have to use kilopascals instead, because that's the units we're using. So, and we do exactly the same principle. Any that are sitting on the bottom, we invert them, swap the signs if there's a surplus on the bottom, and we cancel the units out. So let's have a look. So there they are there. Invert that. So, and what we get is K to the, we get kilopascals to the to the -1, so that means it's it been inverted. So it's kPa to the -1, so the full thing has been inverted. Okay, so no difference there with Kc at all. Okay, so let's look at Kp in heterogeneous equilibria. So we've seen it with homogeneous. So this is to do with heterogeneous ones. So this is so just like with Kc, heterogeneous equilibria for Kp only includes gases. So all the Kp examples that we've seen so far have been for homogeneous equilibria. And so here's an example for writing Kc expression. So you can see here that we've got ammonium chloride, which is our solid, ammonia, which is our gas, and HCl, which is our gas. So our Kp expression is going to be Kp equals PNH3 and PHCl. So remember, with heterogeneous examples, that we emit products that are not in the same state. So, for example, if they're a liquid, or if they're a solid, a pure liquid, or if they're a solid, we emit them in heterogeneous equations. So it's exactly the same for Kp, except what we're going to do is omit anything that is not a gas, and we're going to include gases in Kp expressions. Okay, excuse me. Right, so let's look at an example here, which we're going to look at Le Chatelier's principle. Now, equilibrium wouldn't be equilibrium without Le Chatelier's principle, okay? And you might have seen this before, but we're going to go through it, and we're going to apply Le Chatelier's principle. I'm going to go through, say what it is first, and who this chap is first. And then once we've done that, then we're going to look at then going to look at adapting his principle to some specific examples. And actually, in industry, this is really important. I'll tell you why soon. But Le Chatelier, he developed a principle when he stated what would happen if we change conditions to an equilibrium reaction. Okay, so here he is here, fine chap. So he said, if a reaction at equilibrium is subjected to a change in pressure, temperature, or concentration, then the position of the equilibrium will move to counteract that change. Wow, that seems quite a lot. So basically what he's saying is, if we do something to a reaction, the reaction will try and do the opposite. And that something's going to be pressure, temperature, or concentration. You've got to remember this, though. Don't use that as a definition. You've got to use the formal definition, which is written there. Okay, so if we change the condition, if the change in condition results in equilibrium shifting to the left, we make more reactants. So you can see here what I've done is I've written down an equation, but I've emphasized one side of the equation. So you can see here we've got hydrogen and nitrogen, which is here, and we've got ammonia, which is on the right hand side. But if the change in condition results in equilibrium shifting to the left, we do make more reactants. So in other words, we're shifting it to the left. And likewise, if the change in condition results in equilibrium shifting to the right, we make more products. And you can see that on there, we've emphasized the product side. Okay, so what I've done is I've put Le Chatelier principle at the top there. So I've squashed them up in the top left-hand corner there. Because I think if we keep his principle in mind when we're looking at these examples, I think it helps you to remember his principle, but it also helps you to use it and explain your answers as well. So, if we increase the concentration of a reactant or product, the equilibrium will shift to try and reduce the concentration, okay? And so the opposite will happen if the concentration is decreased. So we're going to look at some different examples here, and this is the first one, which is concentration. So this only works in homogeneous equilibrium. Remember, that's if the reactants and products are in the same state. So if we increase, we're going to look at the same reaction. This is the Haber process. It's the manufacture of ammonia, which can be used in fertilizers in the farming industry, in the agricultural industry. So, but if we increase the concentration of hydrogen, equilibrium will shift to the right to use it up and reduce the concentration, and so therefore we'll get more ammonia is being produced. So let's have a look. Let's break that down. So we're going to increase the amount of hydrogen, so we're going to have more of that. Equilibrium is going to say, equilibrium according to Le Chatelier's principle, as you say, I'm not having that. We've got loads more hydrogen, I'm going to use that up. I don't want more hydrogen in here. So the only way the reaction can use up that hydrogen is by reacting it with nitrogen to form more ammonia. So if you're in the industry of producing ammonia, then increasing hydrogen is not a bad place to start in this example. And if we increase the concentration of ammonia, equilibrium will shift to the left to use it up and reduce the concentration because we've just increased it. So the more hydrogen and nitrogen is produced. So just the same principle, if we increase the amount of ammonia, the equilibrium will shift to try and reduce it, and it will produce more hydrogen and nitrogen. So that's not a good move if you're in the industry of producing ammonia. Okay, so let's look at pressure. So if we increase the pressure, the equilibrium will shift to try and reduce the pressure. So you see, it's just doing the opposite. It's a bit annoying, isn't it? But you can use it to your advantage to an extent. So the opposite will happen if the pressure is decreased. So again, this only works in homogeneous equilibria. So if we increase the pressure, equilibrium will shift to the side with the fewest number of gas particles. And this will reduce the pressure. And in this example here, more ammonia is going to be produced. So let's break that down. So if we increase the pressure, equilibrium will shift to the side with the fewest number of gas moles. The fewest number of gas moles is on the right. We've got 2 moles of gas here, and we've got 4 moles of gas on the left. So if we increase the pressure, it's going to shift to the side with the fewest moles to decrease the pressure. So that means it'll shift to the right. So if you're in the industry to make ammonia, decreasing the pressure is not a bad start. And likewise, if we decrease the pressure, increasing the pressure is going to be the best thing if you're going to produce ammonia. So if we decrease the pressure, equilibrium will shift to the side with the most number of gas particles to increase it. So that means it will move to the nitrogen and hydrogen side because we've got 4 moles of gas on the left, and we've only got 2 moles of gas on the right there. Okay, so if you're in the industry to make ammonia, you would increase the pressure. So that's a good place to start. Okay, and let's look at increasing temperature. Let's have a look at what effect temperature would have. So if we increase the temperature, the equilibrium will shift to try and reduce the temperature, and the opposite will happen if the temperature is decreased. So again, this only happens in homogeneous equilibria. So this one here, we've got to look at the enthalpy change for the reaction. So if we increase the temperature of equilibrium, equilibrium will shift in the endothermic direction to reduce the temperature, so we get more nitrogen and hydrogen will be produced. So you can see here, here's our reaction, same reaction again, but this time we've been given a little bit extra information, and that extra information is enthalpy change. So you can see here, this is a negative value. This is telling us that the forward reaction here is negative. Okay, it's an exothermic reaction. So, and you'll always see that as well. Wherever you see an equilibrium reaction, the forward, if you see a number next to it, like an enthalpy value, that means that that's telling the enthalpy value for the forward reaction only. So you can see here we've got a forward reaction. A reversible reaction, but the forward reaction is exothermic. So if we increase the temperature, it's going to shift to the left because the backwards reaction has got to be endothermic. So if we increase the temperature, it will shift to try and cool it down. So if we decrease the temperature, equilibrium will shift in the exothermic direction, and this will mean that we produce more ammonia in this example here. So if you're in the industry of making ammonia, then decreasing the temperature would actually be a good thing, which is a bit strange. You may think if we increase it, you're going to get more product. That's not the case at all. So in this example here, exothermic reactions, actually cooling them down will produce more products. Catalysts, this is the final thing to do with Le Chatelier's principle, but catalysts have no effect on the position of equilibrium whatsoever. All a catalyst does is speeds up the forwards and backwards reaction equally. It just speeds up the rate at which equilibrium is established. It has no effect on yield whatsoever. So catalysts are there to lower the activation energy, remember, and are there to speed up a chemical reaction as well by providing an alternative route. So they do have a use, but they don't have any use here for equilibrium. So other than speeding up the reaction. So what affects the value of Kp? So we've seen Kp already, so we need to look at what affects that. And we need to know that temperature, we need to know the effect of temperature, pressure, and catalysts on the value of Kp. So with temperature, Kp is only valid for one temperature. So if we change the temperature, this will change the equilibrium pressures, clearly, because if we heat the gas up, the pressure increases because the particles have got more kinetic energy, and they exert a larger force against the surface of the container, which means that the pressure increases. So Kp will change here as well. So if the temperature change causes equilibrium to shift to the right, then Kp will increase. And if the temperature change causes equilibrium to shift to the left, then Kp will decrease. So let's look at an example here. So you can see in this reaction, the forward reaction is exothermic, the backwards reaction is endothermic. And you can see we know why it's exothermic, because our enthalpy value here is negative. It's got a negative value. So if we increase the temperature, equilibrium shifts in the endothermic direction. This is to oppose that increase in temperature. Remember, it will do the opposite. And so Kp will decrease. And if we decrease the temperature, equilibrium shifts in the exothermic direction. That means it'll shift to the right. And so that means that Kp will increase. So we can work that out, because if we look here, think about our expression. Here's our Kp expression. We've always got products on the top, reactants on the bottom. So if we increase the value of the bottom number here, remember it's like a fraction. So if the bottom number increases, then our fraction is effectively going to be smaller. So the value of Kp is going to be smaller. But if the number on the top of the fraction increases, then the value of Kp is going to increase. So just see it as if you're not so strong at maths, let's say, which is perfectly fine. Look at it in a different way and look at the fractions here. See it as a normal fraction. If you think about a fraction, if you increase that bottom number on a fraction, that's going to make the number smaller, isn't it? So see it exactly the same way, because it is just a fraction. Okay, so let's look at pressure. So the value of Kp is unaffected by any changes in pressure, so that's an easy one. And catalysts, adding a catalyst has no effect on the value of Kp. All a catalyst does is speeds up the reverse and forwards reaction equally, and it just speeds up the rate at which equilibrium is established. It doesn't actually affect equilibrium itself. It just means that you'll reach equilibrium much quicker if you had a catalyst in there, as opposed to not having a catalyst in there. So what affects the value of Kc? So we're going to look at temperature, concentration and catalyst for Kc. Temperature, just like with Kp, it's only valid at one temperature. So changing concentrations will affect Kc as well. And so just like with Kp, if temperature change causes an equilibrium shift right, Kc will increase. If the temperature change causes equilibrium to shift left, then Kc will decrease. It's exactly the same for Kp. The example is the same as well, except what we're looking at here is concentrations of substances rather than pressures, gas pressures. So we have an enthalpy value there, so there's no different there. So I won't go through it in too much detail. But just to bring up tie this bit up here, looking at the Kc expression, exactly the same as Kp. If we get a higher value here, so these are, in this case, these are our reactants. And if equilibrium is shifting to increase the amount of these, then the value of Kc is going to decrease. And likewise, if it's going to increase the amount of products here, it's going to shift to the right. Equilibrium is going to shift to the right, then Kc will increase. So exactly the same as Kp. So there's nothing new there. All we're doing is just swapping it for Kc instead. So that's nice and easy. And concentration, again, the value of Kc is unaffected by any change in concentration. Again, this is just like Kp. And catalysts is exactly the same. It has no effect on the value of Kc because it speeds up both the forwards and reverse reaction equally. Okay, and that's it. So that's the full topic on equilibrium 2. Like I say, there's a full range of videos for all of EDEXCEL on Allery Chemistry YouTube channel. Please hit the subscribe button. They're all for free, and just show your support. That would be marvellous. And also, if you want to purchase these slides, you can. You're at complete liberty to do that. So if you click on the link in the description box, you can get a hold of them there as well. But other than that, that's it. Thank you for listening. Okay, bye-bye.